Alright guys, so I'm going to make this short video for you. I wanted to give you a couple of examples. I also wanted to share with you a couple of very special situations that you might come across as you're working through these problems. Okay, so the two situations I want to make sure that we look at are mutually exclusive and independent events. Alright, now mutually exclusive first. So mutually exclusive kind of is just how it sounds. If A is the first circle here and B is the second circle there, then this would be a situation where A and B are mutually exclusive. Mutually exclusive means that there is no intersection, right? There is no intersection at all, that just A and B are completely separate from each other, okay? Now, this means a couple of things. This means that if I were to do the intersection, probability of A and B, you can see that there's no intersection, so therefore the probability of A and B is always 0. Okay? Another thing that would follow from this is that A union B, remember that's where we take everything from A and then everything from B. Well, that would literally just be everything from A and everything from B. Right? And so the union would just be the sum of those two because the intersection is 0. You may remember from our laws of probability that we covered right at the end of class, we said that for any situation, the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B, right? And in this case, the A intersect B is 0, and because that's 0, then the union is just A plus B because there is no intersection there. All right, so this is something that you could use in a situation where they are mutually exclusive. Okay, now a second situation that is kind of a special situation is when events are independent of each other, right? So two events have no dependency on each other. The second one will not change based off of the first one, okay? Now, there's not a specific Venn diagram for this one, but if two events are independent, then a couple of things happen, right? It means that the probability of A and B both happening are probability of A times probability of B. And we've actually used this a couple of times when we were looking at, for example, the dice, right? When we rolled 2 dice, when we said, what is the probability of getting 2 6s, right? Well, the probability that the first die would be a 6 was 1 over 6, and the probability that the second die was a 6 was 1 over 6, and so when I multiply these, I put them together, I get 1 out of 36, which if you were to do the sample space diagram with the grid, right, and you were to figure that out and put 1, 2, 3, 4, 5, 6, you would see that there was one place out of those 36 squares where you could get 2 6s, right? So independent events are ones for which this is the case. Now, something else that follows if two events are independent, then it means that the probability of A is equal to the probability of A given B, right? Now, that should make sense for something that's independent, right? For something that's independent, it shouldn't matter whether B happens or not. If we're not looking at B, if we're just looking at the big picture, then the probability of A should be probability of A. But if we're only looking at things in B, I should still get the same probability for A. If I get a different probability for A when B is happening, then B and A aren't independent. There's some type of dependency where B causes something different to happen for A. Now, this also means that the probability of A given not B also has to be the same, because it shouldn't matter whether B happens or not. Whether B happens or not, the probability of A must be the same in every scenario. And if those things are true, then we can say that those two events are independent. Most of the time, we will assume that events are dependent, or in other words, that there's some type of link between the two, unless we're told otherwise, right? If we're looking at courses like physics, biology, chemistry, those are dependent on each other, because taking one class means that you may be more or less likely to take one of the other classes, right? That's not independent of each other. So we wouldn't use any of these formulas up above. Okay, so these are kind of things to think of. Remember, the big idea for independent is just that the second event will happen exactly the same regardless of whether the first event, whatever the first event gives you. Okay, if changing the first event changes possibilities for the second event, then it is no longer independent. All right, now with that, let's go into a couple of examples. I want to show you, I told you in the class that I would show you a couple of ways that you could use the probability laws that we came up with in class when we looked at those at the group activity there. All right, so Marcello is playing in a cricket match in a game of hockey at the weekend. The probability his team will win the cricket match is 0.2, and the probability of winning the hockey match is 0.6. Assume the results in the matches are independent. Now, if it didn't say this, then we would not assume it. In fact, we would probably assume that they are not independent, just because, if you win one match, then you have positive feelings and a good outlook, and it may mean that you do better in the next match, right? So there shouldn't be an independence there, but they are telling us that we can assume that they're independent. So let's go ahead and do that. So the first question is, find the probability that Marcelo's team wins both matches. So what it's saying is, what is the probability? So A, actually, let's see. Let's do C for the cricket match. So the probability that the cricket match is 1. So C represents win cricket. So we know that the probability of them winning the cricket match is 0.2. All right? And then we also know that means that the probability of winning hockey is 0.6. So therefore, the probability of winning both matches, that would be the probability of C and H, just like that. So we just learned that for independent events, that this is the same as PC times PH, which then is 0.2 times 0.6, which gives us 0.12 probability that they're going to win both matches. All right. The next question is, find the probability that Marcello's team wins the cricket match or the hockey match. Okay, so this would be P, and this is cricket or hockey. Now remember, in mathematics, or means that it could be they win the cricket, or they win the hockey, or they win both of them. Okay? Now, you may remember this is one of our probability laws, is that the union is equal to PC plus PH minus P, C, and H, just like that. Now, because it was independent and because I was able to figure out the union up here, I now have all the pieces that I need, right? I can take the PC and put that in. I can take the PH and put that in. And then I can take the P, C, and H, which was the answer to question number 1, and throw it in right there. So this should be 0.2 plus 0.6 minus 0.12, which would then give us an answer of 0.68. So the probability of winning one or the other is 0.68. All right. Now, number C says, determine if winning the cricket match and winning the hockey match are mutually exclusive. Now, what that means is, if I win the cricket match, then I cannot win the hockey match. Or if I win the hockey match, I cannot win the cricket match, right? Mutually exclusive, remember, means that there is no overlap. Now, we already have all the information that we need. I'm not going to write it down, but I will explain it to you. We already know that there's an overlap, right? Because there's an overlap, there's a possibility of both things happening at the same time. Then no, it cannot be mutually exclusive. And that's because for mutually exclusive, the intersection must be 0. All right? All right, not too bad, right? Let's go ahead and look at a second example where we use this. This one is less of an application question and a little bit more of just being able to use the laws of probability that we've been introduced to. Okay, so this says, let H and G be events such that PH is 1/3, PG equals 3/7, and PHUG, isn't that cute, P-hug, is 13/21. So this time they've given us a significant amount of information. The first thing they want us to do is find the probability of H and G. All right, well, what should be going through your head is, well, I have this, and I have this. Okay, now it does say here, determine if H and G are independent. Now, because it's asking me to determine, I already know that I can't assume that they are. Okay, so you cannot use the independent rule to say, well, that means P, H intersect G equals 1/3 times 3/7. Sorry, you can't do that either. 3/7. This would be incorrect because this only works if we know 100% sure that they are independent. All right, so we're going to get rid of this. We're going to have to come up with some other way to get the intersection. Okay, now you may have recognized that one of my probability laws is the probability of H union G is equal to probability of H plus the probability of G minus the probability of H and G. Now what that means is I have probability of H union G right there. It's 13/21. I have the probability of H. It's 1/3. I have the probability of G, which is 3/7. And then I have minus P, H intersect G. And you'll notice that the only thing I don't have is exactly what I'm looking for, the PH intersect G. And so we should be able to solve that. So I'm going to put everything so it's in 21ths, I don't know how to say that. It doesn't matter. 21 over, sorry, not 21. I promise I can do fractions. We're going to multiply it by 7/7. So that'll be 7/21. You can actually put this into your calculator. You can go like this, and you can make this x, and then you can insolve just like that. I don't have my calculator on my iPad right now, so I'm going to go ahead and times 3. That'll give me 9/21, 13/21, and then that's minus P, H intersect G. And when I put all that together, subtract the 7, oh, that's fancy. Subtract the 7, subtract the 9, I get negative 3/21 equals negative P, H intersect G. And so therefore, P, H intersect G is what I'm looking for, and I got that it is 3/21. No problem, right? Not bad. So therefore, I found P, H, and G. So now I'm ready to move on to the second question, which is PH given G. Now I need to apologize because I think in class I actually wrote this down wrong, because in class I did the probability of A given B, and what this should have been is this should have been the probability of A and B all over the probability of B. And I think I completely wrote down the wrong thing in class, and I apologize for that. Okay, so this is the given formula. All right, And this is one of the laws of probability that we can use, which is what we're going to do right now. So to do the probability of H given G, which is what they're asking for here, what we're going to do is we're going to go ahead and we're going to say, well, that means that we're going to have the probability of, now look on the top, I've got A and B, so both of them together. It doesn't really matter if it's H and G or G and H, because the intersection is the intersection. It really doesn't matter which way we go. Okay, then on the bottom, it needs to be divided by B, and recognize B is the second one. So this is going to be divided by the probability of G, just like that. Okay, so we actually have all the numbers that we need, right? We've got the probability of H and G, which we found right there, which is 3 over 21, or I guess 1 over 7 if we reduce it. And then we've got the probability of G, which is this one right here, which is 3 over 7. And so we should be able to just put those together and say the probability of H given G is equal to 1 over 7 divided by PG, which was 3 over 7. And when I do the math there, I end up getting 1 over 3. So the probability of H, given that G is true, is 1 over 3. Now, the last question is determine if H and G are independent. We've got lots of ways to do that. Okay, the first way is this. We recognize that the probability of H is equal to the probability of H if G is true, or given that G is true. The probability of H was 1/3, and the probability of H if G is true is also 1/3, which is what we just found. That's basically the definition of independent, right? That one thing is not dependent on the other. Well, if G happens or not, it doesn't matter. We get the same probability way. The other way that you could check this is that we could use our law for independent. I could go PH times PG, right? Which is going to be 1 over 3 times 3 over 7, which is going to give me 1 over 7. And if that is equal to the probability of H and G, then it's independent. And we do know that the probability of H and G, we found earlier, was 1 over 7. And because it's the same, then we know it's independent. Okay? You can't use that in the beginning to get the and, or the intersection, because we don't know that it's independent yet. But now that we've proven it, we can say, well, because it's independent, those two things should be the same, and I found them independently, and they are the same. All right, so that's the end of this video. Hopefully it was helpful. Please recognize the formula for the given, which I apologize that I messed up on in class. Thank you very much. I'll see you next time.